If you are new to the channel, then subscribe the channel and press the bell icon for further notification. So okay student, welcome you all to this new lecture in power system series. So today again we will be solving 6 questions from 226 to up to question number 231. Okay, then let's try to solve these questions. Okay, in question number 226, a single phase star connected load is drawing power as a voltage of 0.9, 0.8 power factor lagging. The three phase base power and base current are this much. The line to line load voltage. Okay, so three phase power is given to you, power three phase, that is 100 MVA, and I is given. I, they have not mentioned whether it is phase or line, but you can already feel it because it is star connected. So whatever phase, whatever line, both are equal. So IL equal to IP. So you need to find line to line load voltage. So first you find line to line voltage base value. That means VL base we are calculating. So what is your power, then you will apply. So it is power divided by root 3 VLIL. That is power. Power is equal to root 3 VLIL or 3 VPIP. So here it is 3 into, that is 100. Actually MVA, that's why no cos is coming. It is not P actually, it is S, apparent power. So it is 100 into 10 to the power 6, root 3 into 4, 37.38. So from here you will get your base value, which is 132 kV. Once you know your base value, then they have given the drawing a voltage of 0.9 per unit. 0.9 into its base. So per unit is 0.9. So voltage will be equal to 0.9 into its base value 132. That is voltage line to line we are calculating. So line to line per unit, line to line base. So the answer is this one, 118.8. Now if you see 227, the reflection coefficient of a transmission line is shown in the figure. So reflection coefficient, I will give you one formula. I think you know all these reflection and refraction coefficient. Suppose this is your line and this is terminated in another impedance. Suppose this is Z and actually this should be impedance, and suppose this is terminated another resistance. It can be reactors also or anything. So if it is so, let me first you feel what is your, this is your incident wave. What you do, if nothing is, if you are doing nothing problematic here, it should go in the same way. That is your dotted line. But what happens? Some portions of get reflected. Suppose this much portion is getting reflected. This is reflected wave. The entire thing can also be reflected, but I am taking a small portion. So sum of these two, what would have been original, and now something is going. So what is left here is this one. That is something of this minus this, you can say, or this minus this, you can say. So that's why minus means this side. So this is your refracted or transmission. This one is which is transmitted forward. So from the figure also you can see this plus this will give you this. This is the original incident wave which was supposed to go through this medium. Suppose this is the boundary. This is this point, or junction point. So this was supposed to go the entire line, but it is not going. Some portion is reflected. So this plus this get this one. So you try to remember this. From this figure also you can remember. So actually the reflection coefficient is always Z minus R by Z plus R. Now there are two reflection. One can be voltage reflection, one can be current reflection. So voltage reflection, it is entirely same. So this is coming, and current reflection is negative of this one. Once you remember this formula, rest is okay. So this is reflection coefficient, reflection. So what will be reflection or transmitted is how much voltage will be transmitted forward or how much current will be transmitted. This is always, original was supposed to come, so that plus you reflected. Original is 1 plus this reflected. So it is always this. So for voltage I am directly doing. So no need to remember this one, you can add any time, or if you remember it also, it is no problem. It will be, sorry, actually it is R minus Z by R plus Z. Or you can remember it that way, but in that case you have to put minus there this side. So it is actually R minus Z by R plus Z. Do this correction. So it is actually R plus Z, and if you add Z get cancelled, 2R. And for current it will be again 1 plus this one. So it is actually R minus Z by R plus Z. So remember it in this format. So it is R get cancelled, 2Z by. So you can remember this reflection coefficient, or no need, you add with 1, that with reflection, then will come the reflection. There is no issue. Just you remember this one, R minus Z by R plus Z. Voltage it is same, current it is, there will be minus sign. Now what they are asking you reflection coefficient for the transmission line, this one. So both is same, R and Z both are same, 300, 300. So your reflection coefficient will be 300 minus 300, 0. So for voltage also it will be 0, for current also it will be 0. So that's why it is option C. So it is 300 minus 300, 300 minus 300, both is 300, 300. So that's why it is 0. So you can think for which, or voltage or current, for both it is 0. So no confusion, because they have not mentioned whether it is voltage or current. Now if you see 228, a overhead line having surge impedance of this is connected in series with an underground cable having surge impedance with this one. If the surge of 500 travel from line towards the cable junction. Okay, so for 401, so this line was 401 and now it is terminated at 100 ohm. So a 50 kV, so voltage they are asking, cable junction, the value of the transmitted voltage, transmitted that is reflected, that is 1 plus this u R minus Z by R plus Z. So this is actually 2R by R plus Z. So that is 2 into R means 100, this one is R, this one is Z, divided by 100 plus 400, that is 0.4. So originally it was coming 50, so transmitted will be equal to 50 into this transmission coefficient, that is 20 kV. That is your option B. Now if you come to 229, the total instantaneous power supplied by a 3-phase AC supply to a balanced RL load. I think we have discussed this one in basic electrical circuits. Or you can total instantaneous power, you add all these instantaneous power. If I take Vm Im common, then the first it is Vm sin omega t and Im sin omega t minus that theta power factor angle. For the second phase it is suppose phase A, so for phase B it will be Vm sin omega t minus 120, and for I it is Im sin omega t minus 120 minus that power factor angle, and next one is Vm sin omega t minus 240 and Im sin omega t minus 240 minus the same power factor angle, because it is balanced. If you add all these things, you will find it is a constant value. So that's why your 3-phase AC supply balanced RL load is always you calculate, you will find this is always a constant. So this will actually come 3 Vp Ip cos theta, or that is our original formula of power. So that is always constant. You remember this one, we have already discussed this one. We have derived this one also in electrical circuits. See, I don't know, remember that question number, but you will find it. 230. The insulation strength of extra high voltage transmission line is mainly governed by. So insulation strength. So load power factor no, switching over voltage harmony. So switching over voltage, I think you have seen this one. There is a threshold limit of 345 kV. If below this, we always think for lightning surge, because lightning surge gives an importance phenomena below this. But if it goes above this 300 kV, then before lighting also we think for switching, because switching over voltage is much more higher than the lighting over voltage if it goes beyond 345 kV. So it is extra high voltage, that is around 700 kV or above. So obviously it will be B, option B. Switching we will consider, because it crossed that 345 threshold. Now if you come to 231, consider a step voltage wave of same 1 per unit traveling to a lossless transmission line which is terminates in Z in a reactor. The voltage magnitude across the reactor at the instant of traveling reaches at the reactor. Okay. So across the reactors, that is means the voltage that is going to that side, reactor side, how much voltage is propagating, that is transmitted. So for that you can use this formula R minus Z by R plus Z, or 1 plus. So they have nothing mentioned Z about, so we will consider Z is 0. So put 2 into Jx by divided by Jx, so you will say it is 2. So it is option C. So that is 2, so the transmitted will be equal to 2 into 1 per unit is coming, so answer is 2 per unit. It will be 1 into this factor through which it will be multiplied, how much portion is going forward. So how much portion is going forward? 2. So 2 into 1, 2 voltage you will get. So that is your option C. If you like the video, then press the like button and please give your valuable comments in the comment section.